that our basic instruction cycle is broken up to a series we call pipeline. Okay, this is basically a concurrency. We are doing concurrent task, and we are performing multiple operations at the same time. You can imagine the washing machine example: washer and dryer and folder. Basically, pipeline overlaps various stages of instruction execution to achieve performance. Limitation of pipeline, basically, definitely we have a slowest stage, so it can cause bottlenecks. So we have to wait for that stage to finish, to complete its cycle. Okay, pipelining and superscalar execution. Here we already discussed many times. We have these are the basic 5 stages: instruction fetch, decode, execute, memory access, and write back. How we can accommodate these instructions in different clock cycles. And definitely, in order to alleviate or overcome the pipelining issue, simple pipeline issue, we can use multiple pipelines. We can say superscalar execution. So what happened? It improved the instruction execution rate. Multiple instructions are piped into a processor in parallel, and multiple instructions are executed on multiple fractional units. So we have superscalar, which is the ability to process or issue multiple instructions in the same cycle. This is very simple example that here we can issue more than one cycle. Same thing here. We issue only one cycle per instruction, or one instruction in one cycle. Here we enter 2 instructions in each cycle, because this is a 2-way superscalar execution. So in the example, there is some wastage of resources like error utilization due to data dependency. Here we have a data dependency. For example, NA mean no action. Why no action? Because in this cycle we are waiting for the result of the previous instruction. In this cycle we are waiting for the previous instruction result. So this is we call data dependency. I already give the example. For example, if I say add A, for example, comma B, comma C, it means that take the value from B and C and assign to A. Assign to A. This is one instruction. The value of B and C assigned to C. For example, like this one, like this. A is equal to, if I say B plus C, this instruction. Or if I say next instruction is subtract. Okay, subtract D, comma A, comma E. So in the next instruction, definitely we have to wait for the result of A. Because if we issue this instruction first, okay, because first is instruction fetch and second is instruction decode. So when decode, the second instruction will enter in fetch. Then it go to execute. So this instruction will be in decode instruction. So definitely we have to wait for the result of A, this result. Understand? Add A, B plus C, and subtract D, A plus E, A minus E, for example, A minus E. So A minus E, first we have to wait for the result of A. Understand? This we call data dependency. We are dependent. The next instruction is dependent of previous instruction. or we can say next instruction is waiting for the result of previous instruction. Paham? Yes. Data dependency. That previous instruction A plus B C, A is equal to B plus C, and next is D is equal to A plus A minus E. For example, here, if we clear this instruction, A minus E. So we have to wait for the result of A first. Then, because the output of the previous instruction is the input of next instruction. Faham? Yes. Yes. Any question? Data dependency. Okay, Noor Raida,
No question, sir.
what is data dependency?
Uh, the like the example A will B plus C, then D ni will wait for A to process the output.
Okay. So the previous instruction, and we have a next instruction. So the next instruction is instruction number 2 will be wait for the result of A. Good. Okay. So we have scheduling of instruction is determined by several factors. We have like true data dependency. It means that the result of one operation is an output to the next. Very simple. And number 2 is the resource dependency. Resource dependency means that two operations require the same resource, same hardware, same unit. We call resource dependency. And we have a branch dependency. Branching, like we break the normal execution of the instruction, like loops, like if statement, scheduling instruction across conditional branch statement. There's a condition cannot be done deterministically a priori. It means that so we have a direct dependency, resource dependency, and branch dependency. So the scheduler looks at a large number of instructions in an instruction queue and select appropriate number of instructions to execute concurrently based on these factors. The complexity of this hardware is an important constraint on superscalar processors. Yes. So in a simpler model, instruction can be issued only in the order, in sequence in which they encountered. There is if the second instruction cannot be issued because it has a data dependency like not applicable NA. With the first, only one instruction is issued in the cycle. This is called in order issue that we have to wait. But in more aggressive model, instruction can be issued out of order. In this case, if the second instruction has data dependency with the first, but the third instruction does not, the first and third instruction can be co-scheduled. Both will issue at the same time. Second will issue after this. This is also called dynamic issue. So performance of in-order issue is generally limited. Definitely in order, we have to wait. And dynamic, definitely we can go for next instruction. We can't wait. Very easy concept. Faham? Okay, very simple concept, just theory. Just see. In order issue and out of order issue. In order, we have to wait Out of order, we can't wait. We will issue next cycle, next instruction. Machamana, here, for example, we have another instruction, which is this, G, comma, O, comma, P. Here we can issue this instruction because this is multiply instruction and totally different, totally separate, totally independent. Okay, we can say here G is equal to O into P. There is no dependency. So we can issue this one, third one. And we have to wait for second one. And then we issue this instruction next after this. So if we like give time, so the answer of this will be in the memory. So we can take from the memory. Faham? So not all function units can be kept busy all the times. Definitely, all function can not be busy or sometimes it's busy, but normally not busy because like washer, dryer, sometimes it will free. So we have some type of waste, vertical waste. If during a cycle, no function units are utilized, we call vertical waste. Horizontal waste, if during a cycle, only some of the function units are utilized. Horizontal waste and vertical waste. So due to limited parallelism in typical instruction traces, dependencies or the inability of the scheduler to extract parallelism, the performance of superscalar process is eventually limited. So what happened that also there is a limitation of superscalar execution or superscalar pipelining. So conventional microprocessor typically support four-way superscalar. Four-way means four instructions at a time. So we have another concept we call very long instruction, VLIW processors. The hardware cost and complexity of the superscalar scheduler is the major consideration, major issue in the processor design. So to address this issue, VLIW processors rely on compile time analysis to identify and bundle together instructions that can be executed concurrently. Simple. So what happened in VLIW? It basically rely on compile time, the execution time. So what happened? It will bundle, it will add all the instruction that can be executed concurrently. There is no dependency, nothing. So we can execute all these instructions at same time. So these instructions are packed and dispatched together. Are packed and dispatched mean enter together, and thus the name very long instruction word. The concept was used with some commercial success in a multi-flow trace machine, Kirka 1984. And variants of this concept are employed in the Intel IA64. So we have operation called OP1, OP2, OP1, OP mean operation 1, operation 2, operation 3, operation 4. This is instruction 1, this is instruction 2, this is instruction 3. So we can take any of the operation which have no dependency. Limitation of memory system performance. Memory system and not processor speed is often the bottleneck of many applications. So memory system performance is largely captured by two parameters, latency and bandwidth. So we have two parameters that we can measure the performance, latency and bandwidth. What is latency? Latency is the time from the issue of a memory request to the time the data is available, just available. And bandwidth is the rate at which data can be pumped to the processor by the memory system. Okay, so bandwidth and latency, the time and the rate. We can see the example, very simple. It is very important to understand the difference between latency and bandwidth. Consider the example of a firehouse pipe. If the water comes out of the house 2 seconds after the hydrant is turned on, the latency of the system is 2 seconds because before the start, it's ready to throw the water. We call latency. Once the water start flowing, if the hydrant deliver water at the rate of 5 gallons per second, this is we call bandwidth. And the bandwidth of system is 5 gallons per second. Very easy. Simple example. How to differentiate latency and the bandwidth. If you want immediate response from the hydrant, it is important to reduce latency. 1 second, half second. If you want to fight big fires, you want high bandwidth. Definitely, we want high bandwidth. We need 1,000 gallon water per second. If more water, definitely we can fight a big fire. This is the example of bandwidth and latency. And we have one more concept, cache. Cache is the memory which is reside main memory and the processor. Main memory and the processor. Why we use cache? Basically, cache is a fast memory as compared to main memory. We call DRAM. DRAM is our main memory, dynamic random access memory. DRAM, dynamic random access memory. Why we need cache? Because if we access main memory, it will take time. And main memory is very large, very big memory. Okay, so we want to save the time. So what we can do, we can transfer the most relevant block which are issuing by the processor into cache. Like 500 instruction or 200 instructions, we can transfer in cache memory. And then processor can execute one by one. Why cache is fast? Because cache construction is the same as processor. The elements understand is the same. The construction of processor and the cache is same thing. Or we can say the material of cache and the processor is same. That's why cache is expensive. That's why we can't go large cache. We can use only small caches. Like for example, when I come to class, I will bring laptop. I will bring my bag. In my bag, I can take the most frequent use items like marker, like pen, your attendance sheet, my glasses, my cell phone, because I can use most frequently. I can't take my whole room cupboard at your class. I just bring my laptop big because the important things which I use frequently. And in my office, there are books, notes, handouts, many things. So the office items are just like a main memory. And my bag is like a cache memory. Understand? That's why cache is expensive. Cache is fast. and cache size is small because of its construction cost, the construction material. Understand? You can ask question. Oh, that's now it's a very easy. We can use cache instead of memory. No, we can't use cache instead of memory because if you use, if you remove memory, our system cost will be high, very high, expensive, maybe 3 times of the laptop or 4 times of the laptop. That's why cache is in MB, megabytes, and your main memory is GB, 32 GB, 48 GB, 64 GB memory nowadays. Okay, the fraction of data references satisfied by the cache is called cache hit. Whenever processor got the instruction or data from cache, we call cache hit of the compilation of the system. Cache ratio achieved by the code on a memory system often determines its performance. Whenever a processor got data or instruction from the cache, it means cache hit, and the processor can access that data or instruction rapidly. With the help of buses, you can see on the motherboard, your motherboard have lines, parallel line. These lines are the buses. Okay, we call near the memory bus, we call memory bus or memory units. So memory bandwidth can be improved by increasing the size of memory block. If the size of memory block increase, so memory bandwidth can be improved. Delivery service with a various size of trucks. We have a lot of trucks, okay, small size, large size. If I have, if I want to shift my house to, like, from Sharam to Subang Jaya, many options. I can hire small trucks, 3 small trucks, or I can hire one big truck. So definitely one big truck is okay. It will save time and money. Understand? Very simple example. So the underlying system takes I time units, where I is the latency of the system, to deliver B units of data, where B is the block size. So alternate approaches for hiding memory latency. Consider the problem of browsing of a web on very slow network connection. For example, network connection is very slow. We deal with the problem one of 3 possible ways. We can do prefetching. We anticipate where pages are going to browse ahead of time. We issue requests for them in advance. Like, for example, if our network is very low, what we are doing, we just open 2 3 tabs at once while working with one. So we open another one. So it will be like open fully when we finish our work. We call prefetching. Number one, multi-threading. We open multiple browsers and access different pages in each browser. Thus, we can waiting for one page to load. We could be reading others. Prefetch mean we know the advance which one will be next, so we can open that. And multi-threading, basically more than one browser. We can use more than one tabs or browsers. Spatial locality, we access a whole bunch of page in one go, reducing the latency across various axes. We open all the pages in one. There are three possibilities. So trade-off of multi-threading and prefetching. Multi-threading and prefetching are critically impacted by the memory bandwidth. Definitely, if you open so many tabs, our performance will be slow. So multi-threaded system become bandwidth bound. Yes. Instead of latency bound. So it's memory bound. For example, we have a narrow road. We have a narrow road and we have a lot of traffic, a lot of cars. So that's why I call bandwidth bound. If we have a high speed cars, high speed vehicles, but the road is very narrow, useless. So multi-threading and prefetching only address the latency problem and may often worsen the bandwidth problem. Requires significantly more hardware resource in the form of storage. We can use alternate routes, highways, many highways. Understand? So by doing this, we can control the traffic of the devices. Dichotomy of parallel computing platforms. Based on the logical and physical organization of parallel platforms, logical organization, programmers' view of the platform, basically we call logical organization, and explicitly parallel program must specify two things: parallel concurrent task and the interaction between the concurrent task or concurrent subtask. We'll see next the communication model. And the physical organization, the topology, the actual hardware organization of the platform, logical organization and the physical organization. Basically, programmer will do the task management, synchronization, load balancing. So logical and physical organization. So control structure of parallel program. Parallelism can be expressed at various levels of granularity, from instruction level to processes. Between these extremes exist a range of models along with corresponding architecture support. Processing units, we have processing unit or PE, processing element. In parallel computing, either operate under the centralized control of a single control unit or work independently. The processor itself, we call processing unit. If there is a single control unit that dispatches the same instruction to various processors that work on different data, the model is referred to as a single instruction stream, multiple data stream, SIMD. Again, if there is a single control unit, we have only one single control unit that dispatch, that issue the same instruction to various processors that work on different data. That model we call SIMD. Single instruction stream, multiple data stream. On the other hand, if the processor has its own control unit, each processor can execute different instruction on different data items. The model is called multiple instruction stream, multiple data stream, MIMD, SIMD. Just memorize that concept. This is SIMD and MIMD. A typical SIMD architecture A and a typical MIMD architecture B. You can see we have a global control unit, single control unit, centralized control unit, and on the other hand, we have a individual control unit with the P, along with the P, processing element or processing unit. Very easy difference. Understand? Okay. So SIMD processors SIMD processors, some of the earliest parallel computers such as Iliad 4, MPP, DAP, CM2, these are the name of systems which belongs to the class machine, and variant of this concept have found in co-processing unit such as MMX, multimedia extension, and DSP processor chip at the Shark. So SIM basically relies on the regular structure of computation such as those in image processing. This is the application that we use in the SIM architecture or SIM processors, image processing. These are the name of the machine using SIM architecture. And the MIM, in contrast to SIM processor, MIM processor can execute different program on different processors. A variant of this called single program multiple data stream, SPMD. This is a variant of MIMD. It is easy to see SPMD and MIMD are closely related in terms of programming, flexibility, and underlying architectural support. Examples of such platforms include current generation of SAN, Ultra servers, SGI, Origin server, multiprocessor PC workstation clusters, and IBM SP. These are the MIMD processors. We have variant SPMD and MIMD. Our is MIMD. Our laptops, our PCs are MIMD because it supports multiple instruction and multiple data. Now we'll see the Flynn taxonomy. Flynn is the name of scientist. So there are different ways to classify parallel compute. Now we are classifying the parallel computers. So one of the more widely used classification used in since 1966 is called Flynn taxonomy. What is Flynn taxonomy? Flynn taxonomy is used to classify parallel computers. So Flynn taxonomy distinguishes multiprocessor computer architecture according to how they can be classified along the two independent dimensions of instruction stream and the data stream. Each of these dimensions can have only one of two possible, single or multiple, two states, single state or multiple state. So the matrix below defined four possible classifications. SIMD, single instruction stream, single data stream. SIMD, single instruction stream, multiple data stream. MISD, multiple instruction stream, single data stream. MIMD, multiple instruction stream, multiple data stream. 4. Now we'll see one by one. Okay. SISD, single instruction, single data. A serial non-parallel computer. This is a serial non-parallel computer. This is serial computer, not parallel. Because single instruction, single data. So single instruction, only one instruction stream is being acted on by the CPU during one clock cycle. And in single data, only one data stream is being used as an input during any one class. Deterministic execution, one by one, sequential execution. So examples, older generation mainframe mini computers, workstations, they use this load A, load B, C equal A plus B, store C. So sequential, top to bottom approach. Here, number two, single instruction, multiple data, SIMD, a type of parallel computer. Not fully, but a type of parallel computer. Single instruction, all processing unit execute the same instruction at the given clock cycle. Multiple data, each processing unit can operate on different data element. So best suited for specialized problems characterized by a high degree of regularity such as graphic and image processing. Synchronous lockstep and deterministic execution, two varies processor array and vector pipelines. So here, single instruction and multiple data stream. Basically, this type of parallel computer used for image processing application. If we see down P1, P2, and P3, Pn mean there's a processor. Processor 1, processor 2, and processor N. Top to bottom is a time. For example, this is a previous instruction, any instruction, load, any load, a load B, and any different calculations and different storages. And so what they can do, they can process the same instruction. Same instruction are same at the clock cycle, but with the multiple data. Data is changed. Like here, A1 here, A2 here, B1 here, B2, but load, C, same thing. Same formula. Faham, SIMD, MIMD, MISD, sorry. Multiple instructions, single data. This is also a type of parallel computer. Here, multiple instructions, each processing unit operates on the data independently. And we have different instructions here, but data is same, single data. Okay, few or any actual example of this class have ever exist, but we can say in engineering, yes, in electrical engineering, we use this kind of system that we have multiple frequency filters operation on a single string or multiple cryptography algorithm attempting to crack a single coded message. We have multiple instruction, but data is same. Data is single. MIMD. Multiple instructions, multiple data. This is basically the actual parallel computer. We call supercomputer. So multiple instruction, every processor may execute different instructions. Multiple data, every processor may be working with a different data stream. So execution can be synchronous or asynchronous, deterministic or non-deterministic. Concurrently, the most common type of parallel computer, most modern supercomputer fall into this category. Most concurrent supercomputer, network parallel computer, cluster grades all lie into MIMD. SIMD, MIMD comparison, very simple comparison. SIMD computer required less hardware than MIMD computers. However, SIMD processors are specially designed. They tend to be expensive or have long design cycles. Not all applications are naturally suited to SIMD. In contrast, SPMD paradigm can be built for inexpensive of the shelf components with variety of little effort in a short amount of time. So you can see the comparison SIMD, MMD, all these. So we have some communication model for parallel platforms. There are two primary forms of data exchange between parallel tasks: accessing a shared data space or exchange messaging. Exchange message, two primary form of data exchange. Number one, accessing a shared data space or exchange messages. Platforms that provide a shared data space are called shared address space machine or multiprocessors. Or platforms that support messaging are also called message passing platform or multi-computer. Multi-computer and multiprocessors. Different thing. One is basically shared address space, other is message passing platform between the processors. So we have multi-computer and otherwise multiprocessors. You can see a shared memory multiprocessor. We have a CPUs all shared with the memory. And number two is message passing multi-computer. We have a memory with local memory with the computer, with the CPU, and all are interconnected. And number three, we have a complete system, like we have a wide area distributed system. Full-fledged, we have an internet, and we have a processor, we call CPU, and the memory as well. And all are interconnected with each other via internet. This is a wide area distributed system. And number one is the shared, basically memory multiprocessor. All processors using the shared memory. Here, every processor has its own local memory. It's very expensive. Simple as this. If shared, cheap. Distributed, definitely it will be expensive. Shared address platform. Part or all of the memory is accessible to all processors. Processor interact by modifying data objects stored in this shared address space. This platform is called UMA and NUMA. UMA, Uniform Memory Access, and Non-Uniform Memory Access. Processors have equal access time to memory in the system, identical processors here. This is UMA, uniform, and non-uniform machine. Not all processors have equal access time to all memories. Memory access across link is slower because we have a bus. We have a bus interconnection. Definitely it's slow. UMA and NUMA. So you can see UMA and NUMA, typically shared address space instruction. A basically is uniform memory access shared address space computer. We have a shared address space computer. Another is non-uniform memory access on shared address space computer with local memory. Same thing. Here local memory. Here no local memory, but shared address space. Here, yes, non-uniform access on shared address space, but with local memory. So it will fast and expensive. So NUMA and UMA distinction. The distinction between NUMA and UMA platform is important from the point of view of algorithm design. NUMA machine require locally an underlying algorithm for performance. Programming these performs easier since read and writes are implicitly visible to all processors. However, read-write data to shared data must be coordinated. This is discussed. Definitely, we have to coordinate. We have to synchronize. There is a thread. We will use thread programming. And cache in such machine required coordinated access to multiple copies. This leads to cache coherence problem. Cache coherence means same copy goes to the different caches. Cache coherency. The weaker model of this machine provides an address map but not coordinated access. These models are called non-cache coherent shared address space machine. Anyway, we have two models, NUMA and UMA. And this is basically the definition that processors have equal access time and identical processors. Other is not all processors have equal access time to all memories, but memory access across link is slower. Last is message passing platform. We'll see this in chapter 6 in detail. These platforms comprise a set of processors and their own memory. These platforms are programmed using variants of send and receive messages or primitives using libraries such as MPI library and PVM provides such primitives. Message passing interface we'll see in chapter 6. So this is a cluster computer. See, all systems are combined and make a cluster computer architecture. Multi-computer architecture can be used for parallel computation. And what happened? There is a server node, and all other are basically the client nodes, and all are integrated via Ethernet in the network. So this is message passing versus shared memory space. Message passing require little hardware support other than a network. Processor must explicitly communicate with each other through messages. Data sent among processors cannot be shared if it's copied using send receive messages. Shared address space require more hardware support. Definitely is expensive. Processors access memory through to shared bus. Data sharing between tasks is fast and uniform. So shared address space platforms and message passing platform. So anyway, this is lecture number 2, and then we'll move towards lecture 3 after 15 minutes. Okay, 15 minutes or okay, take rest and we'll start next slides. Okay, take 15 or take whatsoever I will come. Okay, wait, and I will share the lecture number 3 also before starting. Okay, Bismillahirrahmanirrahim. So this is next lecture, which is 3. I already shared in WhatsApp group. Okay. So previous lesson we have seen like the UMA, non-unified memory access, unified memory access, and the flank taxonomy, process architecture, pipeline with superscalar. And this lesson we will see how to handle multiple memory units, like data bus, how to link multiple processor and the memory units. So basically, physical organization of parallel platforms, ideal parallel machine or parallel system are called parallel random access machine. Parallel random access machine or PRAM. So what is PRAM? PRAM consists of preprocessors and a global memory and a uniform memory of unbounded size that is uniformly accessible to all the processors. Processors share a common clock but may execute different instructions in each cycle. Processors share a common clock but may execute different instructions in each cycle. So here PRAM, depending on how simultaneous memory accesses are handled, PRAM can be divided into 4 subclasses. EREW, exclusive read and exclusive write. EREW PRAM, no concurrent read-write operation are allowed. This is the weakest PRAM model because there is no concurrent read-write operations allowed here. And the concurrent read-write, concurrent read exclusive write, CREW, CREW, PRAM. Here multiple read are allowed, but multiple write are serialized. So here you can see in diagram, both concurrent reading and concurrent writing are prohibited. No read, no write. But here concurrent reading is allowed, but concurrent writing is prohibited. Other two is exclusive read, but concurrent write. Multiple write accesses are allowed, but multiple read accesses are serialized. Concurrent read and concurrent write. So what happened here? Yes, here basically multiple read and write accesses are common. The most powerful PRAM model because both are concurrent. So this will be the most powerful PRAM model. So these are the 4 subclasses of PRAM, parallel random access machine, where we have multiple processors but a global memory. This is the algorithm for all the models, but definitely the last one, the performance is very high. Architecture of an ideal parallel computer. If you talk about the ideal parallel computer, there is no bug, no issue. So what does concurrent write mean? Several protocols are used to resolve concurrent write. Common, arbitrary, priority, and sum. Write only if all values are identical. Common. Arbitrarily write the data from random selected processor and rest fail. Priority allow a predetermined priority order. The processor with the highest priority succeed and the rest wait or fail. Sum, write the sum of data items like sum based write conflict resolution model. So these are the protocol basically used in ideal parallel computer. Common, arbitrary, priority, and sum. So we have now we'll see start proper topic interconnection network and network topologies. So you have YouTube videos. You can definitely uh, open that links. So interconnection networks for parallel computers. Interconnection network carry data between processors and to memory. Interconnection network. These are the lines. These are the interconnection that connect processor and memory and caches. Are made of switches and links, wires and fiber. So interconnects are classified as a static or dynamic. So static network consists of point-to-point communication link among processing nodes, which we call direct network. Dynamic networks are built using switches and communication links. Switches and communication links. And dynamic network also refer to a indirect link. We'll see in the diagram next. Yeah, see, static and dynamic interconnection networks. You can easily distinguish that in indirect, we have in between we have a switching elements. And static link, we have a processing elements are directly connected. Direct or static network. Okay, in between we have a switching element and there is no switching element. Switches map a fixed number of inputs to output. The total number of ports on a switch is the degree of switch. If switch has 8 ports, we call its degree is 8. If switch has a 16 port, we call its degree is 16. Understand? So this is the concept of switching. Definitely, the cost of the switch grows as a sequence of degree of the switch. The peripheral hardware linearly as a degree, and the packaging cost linearly as a number of pins. So cost will high. It means cost will high. If you use more switch, definitely cost will high. So this is basically about the switches that here static network we can call point to point or direct networks. But dynamic network we have switches and communication link, indirect link. So definitely it should be expensive, costly. So processor talk to a network via a network interface. How processor interact with the devices? So there's an interface. There is a connector. So a network interface may hang off the input-output bus or the memory bus. The conventional network interfaces hang off the input-output buses. whereas network interfaces is tightly coupled with machine handoff the memory buses. So the relative speed of input, output, and memory buses impact the performance of the network. Definitely, if we have the interfaces or if we have links, higher link or high speed links, so it cost will high. Ultimately, we can get a good performance. This is all about the network interconnection or network interface. Yes, now network topologies, the way in which systems are interconnected to each other. The physical architecture is called topology. The variety of network topologies have been proposed and implemented. These topologies trade off performance of for cost like star, ring, bus, mesh, hybrid, crossbar, omega switch. Commercial machines often implement hybrids of multiple topologies for reason of packaging, cost, and available components. And we can go for hybrid topologies also. I don't want to finish this chapter today. Number one topology is bus. Very simple. You already learned in uh, computer networks or data communication. Some of the simplest and earliest parallel machines use buses. All processors access the common bus for exchanging data. The distance between any two nodes is zero often in a bus because all are interconnected. The bus also provides convenient broadcast media because we use a single link. However, the bandwidth of the shared bus is major bottleneck. Because of shared link, this is basically the major bottleneck. So typical bus-based machines are limited to dozens of nodes, like Sun Enterprise servers and Intel Pentium-based shared bus multiprocessors are examples of such architecture. So this is basically bus topology. See this slide? Okay, don't cry, don't cry. So this is basically network topologies, buses. Okay, so this is the diagram of bus topology. So bus space interconnects with no local cache and with local memory cache. You know, if we use any other hardware, it will be costly, but the performance will be ultimately high. So since much of the data accessed by a processor is local to the processor, a local memory can improve the performance of bus-based machine. So A is just simple bus, processor 0 and processor 1. And we have data bus, we have address bus, and we have a control bus also, shared bus. Here we have a local cache also. Each processor has its own local cache. So ultimately the performance will be fast. Bus is basically how you see the bus. You can see the motherboard of the processor or the system or the computer and see the pair lines. So the pair lines are the buses basically. And we have three types of bus: address bus, data bus, and control bus. Control bus carry the control signal like add, subtract, multiply, load, store, and data for data, and address is for the memory location address. And number two is the crossbar network. A crossbar network uses an P into M grid of switches to connect P input to M output. And definitely it's a non-blocking manner. This is the variant of the topology. Now, this is called crossbar. We have a memory banks or memory blocks, and we have a processing element. So all processors are integrated with the memory. Like for example, a completely non-blocking crossbar network connecting P processor to B memory. All are, see, you can see all are interconnected with each other. So the connection of processing mode to the memory bank does not block the connection of any node to any other memory bank. So each and every processor are integrated with all memory banks. This is a second network we call crossbar network. It uses basically P into M grid. P is processor or processor element, and M is memory blocks. M is basically the memory bank or memory block. All are interconnected. See? Crossbar. This is bus. The cost of crossbar of P processors grows P square. If 2, it will be the connection will be 4. If 4, then 16, like this. This is generally difficult to scale for large values of P. Definitely. If you grow, so it will be complex. So example of machine that employ crossbar include a Sun Ultra HPC 10,000 and Fujitsu 2 VPP 500. This is basically crossbar. So crossbar have excellent performance. Definitely it should be, and poor cost scalability. Buses have excellent cost scalability but poor performance scalability. Multi-stage interconnection network lies between these extremes. So we have another thing which is another topology we call multi-stage network. Because the crossbar, the advantage is excellent performance. The disadvantage is cost. Bus is cheap but poor performance. So multi-stage is the like both the benefits are incorporated in multi-stage. So multi-stage is more scalable than a bus in terms of performance and more scalable than a crossbar in terms of cost. Number 3 is multi-stage. So in between there is a stage of this network of multi-stage network. We have a processors left and memory bank on the right, and between we have a stages of the interconnection network. Stage 1, stage 2, stage 3, like this. It's not the cross, but in stages. Cross connected, which is cost, and the performance of the bus. So one of the most commonly multi-stage switch is Omega network. Omega is also a multi-stage network. This network consists of log P stages, like small stages, where P is the number of input and outputs. And input I is connected to the output J. Understand? So just this is basically the variant is omega. How? This is basically each stage of the omega network is implement a perfect shuffle. We have a left shift. The links in between, how these are interconnected with each other, how we connect all this by using left rotate. Like, for example, we have to differentiate, we have to change the bit of the other side. So that's why we can transfer the data. It's not the, like we say cross connected, it connected, but the scheme is that left rotate. For example, if we see is 000, first one, there's, if we left rotate 000, there will be no result. It's no effect. So left rotate same. If we see the last one, 7, 1, 1, 1, 1, 1, so how we left rotate the bit, it will be the same. Yes, if we see 1, 0, 0, 1, so left rotate, it will be 2, because this one will be in the left side. For example, if we see 2, 0, 1, 0, so left rotate will be 0, 0, 1, like this. If you see the 3, 0, 1, 1, the left rotate will be 0, 1, 1 on the other side. So in such a way, we can do the left rotate. Like for example, here number 5, if you see 5 on the right side, 1, 0, 1, 1, 0, so left rotate will be 1, 0, 1. Anyway, what we will do here, just we implement by using the left rotate. A perfect shuffle interconnection of 8 input and 8 outputs. So 0, 0, 0, 1, 2, this is binary basically. 3, 4, 5, 6, 7, 1, 1, 1, 7, 1, 2, 4. So this is basically the binary. So next we will see the perfect shuffle, and we have few more slides. We'll finish this lecture and start parallel algorithm design, lecture number 4, by next week. So I already shared, you can watch the YouTube videos. I already shared some videos here, video on routing and deadlocks. These are the videos, video on packets. And you have some more videos at the end of this lecture. Where? Yes, there are a few more videos here. Yes, there are a few omega interconnection, distributed switches. Okay. Yes, any question up till now? Yes. Yes.
No question, Doctor.
Okay, if no question, you may leave. Thank you very much. So I already shared lecture number 3 with you. So next week we will finish lecture number 3 and start lecture number 4. And you know, we have only around 7 slides. Okay, we have only 7 slides for all the weeks. So we have to go slowly. Okay, thank you very much. You may leave. Assalamu alaikum wa rahmatullahi wa barakatuh.
Salam, jaga Doctor.
Thank you, Doctor.
Tiga, Doctor.
Thank you, Doctor.
Um,